So this problem right here, we have an end cap, has a radius of r, and is filled at a certain point with fluid, and that fluid is filled from a point from the top all the way down to the bottom, and we can call this height h, right? And in this equation, as we're going down, we're going to use little h for us going down. So we're going down at a certain point at little h. We are taking individual slices at point little h in order to find the total horizontal force pushing against the end cap. So since this is a pressure equation, or since this problem is dealing with pressure, we pull out the standard pressure equation expression. P is equal to rho GH, right? And we're taking that value at different points of that little h. So we're going to need to form an integral GH. And so at these little slices, we're going to be taking that area. And so the area of these little slices would be equal to the width times this by its height, and we'll call that height dh. And so we need to find a way to represent this width. So at different values of h, or little h I should say, the angle between this middle part of the end cap and the radius is actually changing, right? And so as this angle changes, this little width changes as well. So we can actually express this side as r sine theta using trigonometry. But since this is only measuring 1/2 of this length, we need to multiply it by 2 to get this other half right here. And so we can incorporate area. We can incorporate area that is changing at different levels of h as w times r sine theta. Wait, no, I'm stupid. W is r sine theta. And we multiply that by 2. 2 r sine theta for the width times that by dh for the height. And so we can pull out a few constants from this. The 2, rho, and g are all constants in this equation. But little h is changing, sine theta, the angle is changing, and dh, that's also changing. And so this expression is more unique because we are dealing with 2 halves of this, right? We need to measure from 2 halves. Because let's say the fluid is down at this point. We're not going to need this expression here. We're not going to need the forces at this part because there are no forces when the fluid is down here. And so it's kind of hard to express with only one integral. So we're actually going to be using 2 integrals to express both halves of the end cap. I don't know why I wrote h. And so those integrals will have the same expression, but we'll be measuring at different points. So this is the top half. We'll say that this is the bottom, right? And so as we're measuring little h, the heights will change. We're measuring out different heights, right? And so in big H, these 2 values will be changing with whatever height our fluid is at. And so we can measure the height from the center to the top of the liquid as x1, and we can measure the height from the middle of the end cap to the bottom as x2. I don't know why I wrote x2 or x1. And so we need to find values or expressions to replace x1, x2 with so that we can incorporate it into our integral. So how do we find x1? We'll start with that. So with x1, let's say we're taking a measurement of little h from here. So we're taking little h from here. Height, say the overall fluid is here. Big H would be at this point. It goes all the way to the bottom. All right. So we can say that this portion right here, from the center of the end cap to the top of the fluid, this is x1. We need to find this value, right? And so in order to do that, we can say that this total height of h minus little h minus the radius will give us x1. So we have big H, then little h. This takes out this portion of the end cap, and then minus r. And r, oh wait, I measured r from the wrong point. R goes from here to here. That's my bad. And so r is this length right here. And so when we subtract that from big H minus little h, that gets rid of that length. So we're left with x1. So x1 will be equal, come on, x1 will be equal to big H minus little h minus r. So how do you find x2? So we're going to draw the same type of scenario, right? So we need to find x2, right? Let's say we're measuring that fluid at a point here. So we're at the top of the, we got the fluid measuring all the way down to here at this point. Total height is equal to big H. We need to find x2, right? So this one's a little trickier, but we can say that this gap right here, this gap is equal to big H minus little h, this small gap right here, right? And then we have the radius going from the center to the top of the end cap. This is radius. And so in order to find that, we take the radius and subtract this by h minus little h. And so that'll eliminate those two lengths, and we're only left with the length of x2. And so x2 will equal r minus big H minus little h. But we still don't have a way to incorporate this into our equations because, well, x1 and x2 aren't in them. And so that's where we can mess around with sign in order to incorporate the x1 and x2 into our top and bottom integrals. So going back to this figure, x1 and r, we can use that. So we can actually say that cosine of theta is equal to x1 over r, adjacent over hypotenuse. We got that. We can then use the trig identity, cosine squared theta plus sine squared theta is equal to 1. Right? And since we need to replace sine, we're going to isolate that in our equation. So we have sine theta, 1 minus cosine squared theta, but since we want to get rid of that square root, or that square, power of 2, whatever you want to call it, we got to square root both sides, and we get sine theta is equal to square root of 1 minus cosine squared theta, right? And so then we can incorporate this cosine into this, but only after we take it to the power of 2. So we have 1 minus x, I don't know why I did that, 1 minus x1 squared r squared. And we can simplify this even further by assuming that r1 is equal to r squared over r squared. Those are equivalent values. And then x1 squared minus r squared. You can combine these two fractions together. And so the entire bottom half will just be r squared. And all of this is being square rooted. So we can simplify this a little bit. We have r squared minus x1 squared, all of this over r, which has just been square rooted. Right. Oh, I almost forgot. I just noticed. Sine theta, I forgot to put in the r. That would be the width of it. Yeah, I almost forgot to do that. And so with that, we can incorporate this expression into our integrals, right? And with this, you can interchange x1 and x2. It will give you the same final expression to put into sine theta. So we can finally start substituting in this expression and replace sine theta. Got h times r times this by the square root of r squared minus x1 squared, all of this over r, times this by dh. And the same thing can be done with the bottom half, 2 rho g little h r squared minus x2 squared square rooted all over r times this by dh for the bottom half. And so we can cancel out some values. R's can cancel out right here. And I am running out of room. Oh my goodness. Square root of r squared r dh. Okay, so like I was saying, the r's can cancel out, and we can substitute in those values of x1 and x2 into x1 and x2. We can derive or put in these equations into x1 and x2. So let me write this before I forget. x1 is equal to big H minus little h minus r. x2 is equal to r minus h minus little h. So we can plug those values in. 2 rho g h times this by r squared minus x1 h minus h minus r squared dh. That's the top half. 2 rho g h r squared minus r minus h squared dh. And so we are almost done with this. We just need to find the integrals or the bounds of integration for these two equations. And so we have, again, the top and the bottom. So for the top half, let me draw another diagram for this scenario. So the top half, we're focusing on these points right here. And so we have the fluid at a certain point, right? And so we're only focused on the top half for the top half. So for this first integral right here, we need to focus on the top of the fluid going down to the center of the end cap, right? And so we can say that little h, since we are taking the measurements of little h, these bounds will be in terms of little h. So the first part of our bounds will be 0, all right? And this is h is equal to 0. And so then we're going down to this center part of the end cap, right? So again, from the top of the fluid to the bottom of the full figure is big H. So we need to find this part right here, right? And so this is at a height of h minus r, because we can take this length of radius right here, subtract that h, we are left with h from this point, top of the fluid, to the center of the end cap. So the next part of the top integral will be h minus r. So bounds of integration will be going from 0 to big H minus r. And so at the bottom, very similar idea, our first part of our integration, since we're starting from here, we're still going down to the very bottom. This one's a little easier to understand. We're starting from the center, which again is h minus r, and then since we're going down the full length of h to the very bottom, that'll be our second part of the integral. And so this entire expression gives us the horizontal force of the fluid pushing against the end cap.